Hi, this is the complete lesson in solid materials focused on Edexcel IAL Unit 1 syllabus. See the description of this video, all the useful links related to my other videos are given. Also, by using the playlist of this channel, you can navigate to any video you require. All my videos, around 122 or 23 videos, are classified into different groups like Unit 1 lesson, Unit 1 past paper discussion, Unit 2 lesson, Unit 2 past paper discussion, like that. I classified them. So by using the playlist of this channel, you can navigate to any required video. Okay, so first we should know that force can interact with solid. So depending on the way it interacts with the solid, the force can cause different types of deformations in the solid. Different types of deformation, I mean the way it interacts can cause different types of deformation. For example, if the force is exerted on the material such that it's a stretching force, we call tensile force, it will extend the material. That means it will make the length of the material to increase. Mostly in your syllabus, the questions are based on wires and springs. So I'm not going to draw any random shape of the materials. Any examples will focus on either wire or spring or rod. Rod is something like a wire, is it? So say for example, imagine a wire or rod, something like this. It's an enlarged diagram. It could be a wire or rod. So if the applied force is a tensile force means that will stretch the material. That means the atoms of the material will tend to move apart. That is called tensile force. So if the force is applied like this, this is we call stretching force or tensile force. There will be extension in the material. So this is a tensile force. So the material is under tension. So there will be tensile force that will cause the material to stretch. There will be extension. Same way, second I can say if the material is under compressive force, the compressive force will make the atoms of the material to get closer to each other. This is called compressive force. Compression. So this is compression. Compressive force. Third part, so there the materials atoms will get closer, there will be compression, it will be compressed, the material will be compressed. The third possibility that's not in the syllabus, it's called torsion or torsional force. That means it will try to twist the material, so it's difficult to draw. So it's like something like the material, one end is fixed, this end is fixed, this is a fixed end, or you can exert a force like this, twisting force. Like this is twist, you twist it this way, the force is applied this way, a twisting force. So when you twist the material, something like if you take my wire and twist it, one end you apply a force in one clockwise direction, other one anti-clockwise, and so that's the torsional force. That's called torsional force. So the next thing is called shear force. That means fourth one, the force is applied parallel to the layers or parallel to the surface of the material. Imagine something like a rod or something like this, a rectangular shape. A force is applied on its surface, this direction, a force F, and in this surface, the force is applied this direction. So this is shear force. This will make the layers of atoms or layers of the material to slide on each other. This is shear force. In your syllabus, we don't consider these two situations. So in your syllabus, we consider only these two situations. There is a tensile force and compressive force we consider in your syllabus. Okay, so we consider only tensile force and compressive force, or tension and compression. So under one of these force, or during an object is solid material is under tensile force or compressive force, there will be deformation. The deformation could be classified into two different types. One is called elastic deformation, the other one is called plastic deformation. what do you mean by elastic deformation? Elastic deformation means when the force is applied, the material will deform. When the applied force is completely removed, or that means when the applied force becomes zero, the material will return to its original shape. For example, if you have a spring, think about a spring. A spring is hung from a firm support. This is the natural length of the spring. We don't consider the mass of the spring, it's a light spring. When you attach a mass to it, or when you apply a force, or when you attach a weight slot, the spring will extend. So this is called, if the spring is at rest after you applied it, this is called static extension. This extension is called static extension. So there will be extension because of the tensile force. The attached mass, the weight or mass, will stretch the spring, so there will be tension in the spring and there will be extension. But when we remove the attached weight, the spring will go back to its original shape. The spring will come back to the same initial length. So that type of deformation is called elastic deformation. Elastic deformation is shown not only by spring, even a wire can show elastic deformation. Like a copper wire, you can have a copper wire hung from a roof. Initially it has a length this much. When you apply a force by using a weight slot, the wire will extend to this particular length. So this is the extension, this is the extension, static extension. Static means no motion, just extends and stays, so we call extension or static extension. Now when you remove the applied force, the wire will return to the same initial length. So this type of deformation is called elastic deformation. Spring, wire, even certain other material like a rubber band also, a rubber or rubber band also shows elastic deformation. When the force is applied, the rubber will extend. When the applied force is removed, the rubber band or rubber will return to the initial length or initial shape. There will be elastic deformation. Something like even you can see even other materials other than spring, metal wire, rubber, metal rod. Other than that, certain materials, something like even bamboo tree, when there is wind, when there's breeze, the bamboo tree or taller trees, they move, and when there is no wind, they come back to the original shape. So they show elastic deformation. These all are called elastic deformation. Elastic deformation means when the force is applied, there will be a deformation. It could be a compression also. I took an example extension, even a compression. When you think about a spring, this is the spring. When you apply a compressive force to the spring will be compressed like this. When the applied force is removed, there's initially the spring is like this. When the force is applied, it compresses like this. When the applied force is removed, it will return to the initial shape. So during compression also, materials like spring, wires, they don't obey compressive force because they will bend. So we don't consider the compressive force of a wire. But if it is like a pillars or something like a thick metal rods, something like imagine a metal beam, something like a thick metal beams, yes, they can show compressive force under compression under compressive force. So there also they will show elastic deformation. So elastic deformation is true for both tensile force and compressive force. When the applied force is removed, the material will return to the original shape. Okay, so the materials those obey elastic deformation are called elastic materials. The next type of deformation is plastic deformation. So plastic deformation means when the applied force is removed, the material won't come back to the original shape, or when the applied force is completely removed, there will be a permanent deformation. The material won't return to the initial shape or original shape. The materials those show elastic deformation also will show plastic deformation beyond a limit of force. So the limit of force, the maximum limit of force beyond which they show a plastic deformation is called elastic limit. So the materials show elastic deformation only up to a particular limit of force. Beyond that force, all the elastic materials show plastic deformation. But there are certain materials, they almost never show elastic deformation. For example, clay. Clay never shows elastic deformation. Might show a little bit, but mostly up to our vision when we see, mostly clay shows only plastic deformation. But a spring, wire, metal rods, they all show elastic deformation up to a limit of force, and if the applied force is more than this limit of force, they will show plastic deformation. So that means the materials will have a permanent deformation. Okay, so when we plot a graph of applied force extension, we normally show the force on the y-axis and the extension on the x-axis. That's the way normally we draw force on the y-axis and the extension on the x-axis. With the extension or compression, most of the materials, the variation or the relationship is almost the same. So I'll consider extension. So if you apply a force and extension graph, extension, normally denoted by delta x, extension. This is the force, the applied force. It could be tensile force or compressive force. Even I use the word extension. This is true for compression also. Some books, they don't use the word extension. They just put delta x. So delta x means it's a extension or compression, but I wrote it extension, doesn't matter. So there are the materials, when you apply a force against extension, even when they obey even when the deformation is elastic, there could be two different types of relationships. Say for example, there are materials, something like most of the springs and almost all springs and the metal wires, their elastic deformation, it obeys a straight line. Up to a particular limit of force is a straight line. Beyond that limit of force, there will be a straight line portion. Beyond that, they will start to curve, but still, if you apply a force, they extend and return to the original shape. So only up to a certain force, the graph force against extension will be a straight line, or we can say force is directly proportional to extension. You can do it by practical and see. Beyond that particular limit of force, the graph will start to slightly curve, the graph will start to bend or curve, and even after up to a certain force here, when the applied force is removed, it will return to the original shape. Then beyond that, there will be a permanent plastic deformation. There will be a permanent deformation. It could be a curve like this, or it could be different shape of curves depending on the type of material. So, but here the first important thing, up to a certain limit of force, there will be a straight line, that is force is directly proportional to extension. Beyond that particular limit of force, the graph will slightly curve, but still up to this force, when the applied force is removed, it will return to the original shape. Beyond it, there will be a plastic deformation. So this region is called plastic flow. Beyond this limit of flows, this region is called plastic flow. Up to that point, the deformation is elastic deformation. This limit of force, where the end of the straight line portion is called limit of proportionality, denoted by L. L stands for limit of proportionality. That happens at the end of the straight line. But even beyond the limit of proportionality, up to a point we call, normally with E, we can use E, that is the elastic limit. So up to E, when the applied force is removed, the material will return to the original shape. Up to L, which is called limit of proportionality, the force is directly proportional to extension. This is true for, generally this is true for spring, this graph is true for springs, metal wires and metal rods also. Metal rods, metal wires and springs, mostly they show this type of deformation. But there's a material, you know, rubber that shows elastic deformation up to a limit of force, but it never shows straight line portion. It does not have any limit of proportionality. So this is for rubber. The graph will be something like this. This is for rubber. It has elastic limit. It has elastic limit, but it does not have limit of proportionality. Rubber never obeys a rule such as force is directly proportional to extension. Is not true for rubber, but it has elastic limit. When you remove the applied force, it will return to the original shape. This is for springs. Elastic limit of proportionality L, up to which the graph is a straight line. That is force. This means force is directly proportional to extension. Then E is the elastic limit, beyond which there will be permanent deformation. If the applied force is more than this limit of force, this particular limit of force, there will be permanent deformation, that is plastic deformation. Okay, next is Hooke's law. Okay, so we came across that materials can have different type of deformation, elastic deformation, plastic deformation. The materials, when they have, when they show elastic deformation up to a limit of force, the force is directly proportional to extension, and I showed it, the graph will be a straight line. So if force is directly proportional to extension or force is directly proportional to compression, so the graph will be a straight line to the origin. Beyond that, the graph will start to curve up to a limit of force or elastic limit. When the applied force is removed, it will return to the original shape. Okay, so for rubber, I showed it never shows a straight line through the origin, but it has elastic limit. Remember that for rubber, because it's a polymer. We don't need the actual reason. It's actually material science. We don't need it. Okay, so what is Hooke's law? Hooke's law is something related to about the relationship up to the limit of proportionality. Already told that up to limit of proportionality, force is directly proportional to extension or compression. I told that. But when you think about the applied force, and say for example, think about a spring, very simple example, spring. This is the natural length of the spring. When you apply a force to the spring, spring will extend. Force means, imagine you attach a weight slot to it. So there will be extension. And when you draw the free body force diagram for the same figure 2, for this figure 2, if I draw the free body force diagram, this is figure 1. For figure 2, if I draw the free body force diagram, draw the spring, not complete free body force diagram. I am going to draw the third block as mainly the reason. So this is the attached weight. Okay, so the weight acts, the weight of the attached weight slot acts on it. That acts downwards, mg. So due to this weight, the weight will try to move down, fall down, but it's not falling. It will exert a force on it. That is called tension. It will exert a force on the spring, a stretching force. That is tension. According to Newton's third law, when the weight exerts tension on the spring, spring will exert the same magnitude of tension in the attached weight. So these two will have the same magnitude. opposite direction. They are Newton's third law pair of forces. Okay, you know that the extension of the spring, when you think about this is the natural length, so the extension of the spring is downward direction. The extension of the spring is downward direction. The force exerted by the spring on the object or force exerted by the spring on the attached mass is upward direction. You can see the direction of the extension of the spring and the direction of the force exerted by the spring on the weight slot, they are in opposite direction. So this also included in the Hooke's law. What Hooke's law says? Hooke's law says force exerted by the spring is directly proportional to extension of the spring. Hooke's law is not saying force experienced by the spring is directly proportional to extension of it. He didn't say that. It says that force exerted by the spring is directly proportional to extension of it. Normally, when we write the Hooke's law, tension, we don't write T, we put it as F. So it's a tension, but I'll show it as F, tension or compression. So I use the word F, notation F. So the Hooke's law says that force exerted by the spring is directly proportional to extension. So force exerted by the spring is directly proportional to extension, but we know that force exerted by the spring is upward direction, extension is downward direction. They are opposite direction among them. Therefore, when we relate it, there should be a minus sign. But we don't use the minus sign when we do any calculation. We ignore the minus sign. But actually, when we write the equation, there must be minus sign. They could ask the exam, they could ask what's the meaning of minus sign. The meaning of the minus sign is force exerted, the direction of the force exerted by the spring and the direction of the extension of the spring are opposite to each other. Same way you draw it and see when you compress a spring, force exerted by the spring, when you are compressing a compressing a spring, there are also, that is true, force exerted by the spring is directly proportional to amount of compression. There are also force exerted by the spring and the direction of compression will be in opposite to each other. You can draw and see that. Okay, so that's the reason of minus sign here. You know, when we convert proportionality into an equation, there must be a constant. So there is a constant minus k, this minus sign k into delta x. This is the equation we use for Hooke's law, but when we use for calculation, we use F equal k delta x. We ignore the minus sign. So this is the equation we use for calculations. K is called spring constants for springs, and for other materials, those obey this law, force directly proportional, something like wires, rods. K is called force constant. For springs, K is called spring constant, and for other materials such as other objects such as wires and rods, K is called force constant. Okay, so you must know that F equal K delta x. I didn't write the minus sign because we don't use that when we do calculations. So for spring, K is called spring constant. For other objects such as wire and rod, we call K as force constant. Okay, so when we consider K, what's the meaning of K? What does it indicate? K indicates, or the force constant or spring constant indicates the stiffness of the object, stiffness of the given object, whether what is the stiffness of the given spring, or what is the stiffness of the given wire, what is the stiffness of the given rod, like that. K indicates the stiffness of the given object, not the material. So K depends on, in which factors K depends? K depends on the type of material and the dimension of the object That means the thickness of the rod or thickness of the wire or the length of the rod, length of the wire, they all decides the K. So K depends on type of material. What type of metal? There could be two different springs. They have the same exactly identical shape, identical thickness of wire, but one is made of aluminium, the other one is made of copper. They will have different K, different stiffness because the materials are different. Or there could be two different springs, both are made of copper but they have different dimensions, so they'll have different K, different spring constant. So remember that K depends on the type of the material as well as the dimension of the material, thickness of the wire used to make the spring, or thickness of the wire, thickness of the rod, length of the rod, length of the wire, everything they decides the value of K. K indicates the stiffness. So stiffness means how much it can oppose or resist the deformation. So higher the K, when K increases, or if there are two materials with different K, there are two springs with different K, higher the K, it is more stiffer. I can say higher the K, more stiffer means more force is needed to have the same deformation. For example, imagine there are two springs X and Y. There are two springs X and Y. One has higher K, this spring constant is K1, this spring constant is K2. So they have different Ks, that is K1 greater than K2, that means this is more stiffer than this one. The spring X is more stiffer than spring Y. What do you mean by that? When you apply the same force, extension will be smaller here, extension will be larger here. Smaller the or lower the K, greater the extension for a given force, easy to deform. Stiffness higher means difficult to deform, so the extension or compression will be lower. What is the unit of K? F equal K delta X. So unit of F is Newton, unit of delta X, SI unit is meter. So unit of K will be Newton per meter. Okay, so if the force extent graph is a straight line only up to here, this is the limit of proportionality. So the gradient of the linear portion, you know, F equal K delta X. F is on the y-axis, delta X is on the x-axis. So the K is given by the gradient. If you find the gradient of the linear portion of the graph, that gives the force constant K or spring constant K, or generally I can say the gradient of the linear portion gives the stiffness of the given object. Okay. Normally they ask, does rubber obeys Hooke's law? No, rubber never obeys Hooke's law. The reason, the force extension graph never has straight line through the origin. So there is no straight line through the origin. So force is never directly proportional to deformation delta X. Therefore, rubber never obeys Hooke's law. So the gradient of the linear portion gives the stiffness K. Okay, so if you do the practical to measure the extension for different forces, imagine you have two different wires made of same material, two different wires made of same material, and both wires have the same area of cross section, and they are made of same type of materials, but they have different length. So if you apply different forces and measure the relevant extension, if you plot a graph on the same axis, two different wires, imagine there are two different wires, wire X or wire P and wire Q, both have same area of cross section, but wire Q is longer than wire P. Both have same type of material. Wire Q is longer than wire P, but both have same area of cross section. If you do a practical, apply different forces and measure the corresponding or relevant extension separately for these wires, and if you plot a graph of force against extension on the same axis, you will get a graph like this. Both graphs will pass through the origin. If you do the practical within the elastic limits, both graphs will pass through the origin, but they will have different gradient. That means they have different stiffness. They are made of same material, only different is they have different length. So there, the longer wire will give a lower gradient, that is lower stiffness, and shorter wire will give greater gradient, greater stiffness. It could be an MCQ question. Remember that. Same material, same type of material, same area of cross section, but one wire is longer, other one is shorter. If you plot the force extension graph on the same axis, longer wire will have shorter gradient, that means less stiffer. Shorter wire will have greater gradient, that means more stiffness. The reason I'll explain later when I start Young modulus. Okay, think about another experiment where both wires have the same initial length L or same initial length X, both have the same initial length, but wire P is thicker, or the diameter of the cross-sectional area of the wire P is greater than cross-sectional area of the wire Q. Both are made of same material. There also, if you do a practical, apply different force and measure the relevant extension, and if you plot a graph of force against extension, you will get a graph like this. Thicker wire will have, or the wire with larger cross-sectional area will have larger gradient, and wire with smaller area of cross section will have lower gradient. That means wire with larger area of cross section is more stiffer, wire with lower area of cross section has lower stiffness, but both are made of same type of material. So remember, this also could be an MCQ question comparing two different types of stiffness made of same type of material. So the dimension also decides the stiffness. Okay, now consider another type of analysis. There we consider same length of wires with same area of cross section. That means exactly the same dimensions. Both P and Q, they have the same, exactly the same dimensions, but they are made of made of different type of materials. One is made of steel, P is made of steel, Q is made of copper. Same length, same area of cross section, different types of material. P is made of steel and Q is made of copper. There, if you plot a graph, force against extension, you will get a graph like that. That is P, which is made of steel, will have larger gradient, means that is more stiffer than the wire made of copper. Yes, this also can be explained when I start Young modulus. By using that, we can explain this behavior also. Okay, so this experiment gives an interesting results. Imagine there are three different wires. They have different lengths, different natural length or different initial length, L1, L2, L3, and they have different area of cross section, A1, A2, A3. Imagine this A3 has much larger area of cross section. Then next is A1, the smallest area of cross section is A2. In terms of length, this is the largest length, this is next length, this is the shortest length. But they all are made of same type of, the same type of material, maybe copper or aluminium, whatever it is. They all three are made of same type of material. Now do experiment, apply different force and measure the extension. Then plot a graph for P such that on the y-axis force per unit length, force per unit area. That means you apply a force each time, say for example you apply different forces like 10 Newton, 20 Newton, 30 Newton, like that. Each force when you apply divided by its area of cross section A1, and that should be on the y-axis. X-axis is extension per unit length. That is, each time when you apply different force, you got extension. Divide each extension by its natural length or initial length, and take that as the x-axis. Extension per unit length, where unit length means each extension must be divided by the initial length, which is L1. And plot a graph, you will get a straight line through the origin. Imagine we are not passing beyond the elastic limit. We are within the elastic limit. So we will get a straight line through the origin. Okay. Now do the same experiment for the next wire L2. All three are made of same type of material. The next wire L2, which is longer than L1 but thinner than L1. This wire Q is longer than P, but area of cross section is A2 is smaller than A1. Here also do the same experiment. Apply a force, divide the force by area of cross section A2, measure the relevant extension, divide the extension by its initial length L2. Like that, different forces are applied, and each force when you apply, divided by area of cross section, measure the extension, divide by initial length L2 and plot a graph. You will see that graph also exactly overlap with the graph drawn for P. That means both have the same extension, same stiffness. Both have the same stiffness. Now think about the third wire, which is thicker and longer, that also made of the same type as P and Q, the wire R. For that also repeat the same experiment, apply different forces and measure the relevant extensions. Each force applied must be divided by area of cross section, that is the y-axis. Each extension must be divided by initial length L3, and plot a graph on the same axis what you plot already for P and Q. You will get the same graph that also will overlap with the earlier two graphs. Already P and Q are overlapping. The graph R also will overlap. That means all these three materials have the same stiffness. That means the stiffness of a material does not depend on the dimension of the materials. Stiffness of a material, careful, what I explained earlier, when I consider force against extension, there I already drew different type of graphs, P and Q I compared. So there the stiffness depends on the dimension of the materials also, even for the same type of material. But here when you draw a graph of force per unit length or force per unit area against extension per unit length, there the gradient is the same, means the stiffness does not depend. Here the stiffness, the gradient does not depend on the dimension of the material. The gradient is the same. That means it's the common property for all the three wires made of same material, different dimensions. That means there's a conclusion we can say the ratio of force per unit area divided by extension per initial length is constant for a particular type of material, that is called Young modulus. This ratio, force per unit area, the ratio between force per unit area and extension per unit length is constant for a type of material, that is called Young modulus. That indicates the stiffness of the type of a material. If you do the same experiment, three different wires, imagine this practical is done, all are made of aluminium, you will get a graph like this. Now do the same like this, same experiment with different length of steel wires. There if you plot a graph for steel wire, you will get the graph with larger gradient. This is for steel, you will get it. This is for copper, you will get it. That means steel, you will have larger gradient, but that also does not depend on the dimension of the wires. So for a particular type of material, you will see that the graph is the same regardless of the dimension of the materials, means they have a property, that is the property of the material, that is called Young modulus, that is the ratio of force against force per unit area against extension per unit length is a constant because they all have the same gradient. This is called Young modulus. different types of materials will have different gradient. Material that has greater gradient means it is more stiffer. The material is more stiffer. For example, if you do the same experiment for copper, we already did it. If you do the same thing for steel wire, different steel wires, they are also, if they are all made of steel wire, that they all graph will overlap with each other, but steel wire will have larger gradient. That means steel is more stiffer than copper. So here this is actually a very useful property of the material, because regardless of the dimension we can compare the stiffness of the materials. That is given by Young modulus. So what is Young modulus? Force per unit area, the ratio between force per unit area and extension per unit length. We have special name. Force per unit area is called stress. Generally we call stress. If it is a tensile force, that is called tensile stress. If it is a compressive force, that is called compressive stress. This is called, could be a tensile stress or compressive stress. This is called strain. Extension per unit length is called tensile strain, or if it is a compression, it's called compressive strain. It could be tensile stress over tensile strain, or compressive stress over compressive strain. That gives the property of the material, that is called Young modulus. Young modulus indicates the stiffness of the material. So the Young modulus gives the stiffness of the material regardless of the dimension of the material. Very important conclusion. Okay, you must know that tensile stress, I already used that word. Tensile stress means tensile force over area of cross section. Notation is sigma. F over A, unit is Newton per meter squared, force per area or Pascal. Same way compressive stress, compressive force over area of cross section, same notation, sigma. F over A, unit is Newton per meter squared or Pascal. Okay, so the next thing you should know is breaking stress or ultimate tensile strength. Breaking stress is the maximum stress the material can withstand, or the sample can withstand, not material, the sample can withstand before breaking is defined or is called breaking stress or ultimate tensile strength. It's given by the equation. So breaking force over area of cross section. So what is breaking force means? The minimum force required to break the material. Minimum force required to break the material is called breaking force. Breaking stress is the maximum stress the material or the sample can withstand before fracturing or breaking is defined as the breaking stress or ultimate tensile strength. It's given by breaking force over area of cross section. So for a given area of cross section, the force that is required to break divided by area of cross section, or for a given force, also we can find for a given force what could be the minimum area of cross section of the wire or rod. Sometimes they ask for a given force what could be the minimum area of cross section, or what is the minimum area of cross section of the wire or rod, whatever they ask. That also breaking stress equal F over A minimum. So either way we can get a question related to breaking stress. The unit is same as Newton per meter squared. So the next two things you should know is tensile strain and compressive strain. Tensile strain is defined as extension over original length. Both have the same unit, so no unit, the tensile strain. The notation for tensile strain is epsilon equal delta x is the extension, x is the initial length or original length. Same way compressive strain equal amount of compression over original length. So the same notation we use for compressive strain also, epsilon equal delta x over x, that also has no unit. You must know, but it's given in the data sheet, better to remember them. I already explained that the ratio of force per unit area over extension per unit length is constant for a given type of material. That is called Young modulus, the ratio of force per unit area to extension per unit length, that is stress to strain, is defined as Young modulus. Generally we can say Young modulus equal to stress over strain, but sometimes book says Young modulus equal tensile stress over tensile strain, or compressive stress over compressive strain. Young modulus is tensile stress over tensile strain or compressive stress over compressive strain, but generally we can write stress over strain. Young modulus is denoted by capital E. Different books here use different notation. Some books they use capital Y, but in your textbooks they use capital E for Young modulus. Stress over strain. So Young modulus, the unit of Young modulus, epsilon, that is stress, the strain has no unit. So the unit of the Young modulus is same as unit of the stress, that is Newton per meter squared or Pascal. Also remember, this equation is valid only when the material obeys Hooke's law. That is, when the stress over strain graph is a straight line only, you can use this equation. So this equation is valid only when the material is within the limit of proportionality. Only when with the material is within the limit of proportionality. So when the material passes the limit of proportionality, you can't define the stress by using, you can't define the Young modulus by using stress over strain. So the material's behavior will change. I told that already. Young modulus is one of the property of the material. So if the material passes beyond the limit of proportionality, its property will change. So there we don't calculate the Young modulus. So if you plot a graph of stress against strain, it will be a straight line through the origin. For example, we rearrange the equation such that stress is equal to cross multiply Young modulus times strain. This is in the form of y equal mx. So if you plot a graph of stress against strain, it will be a straight line through the origin. The gradient of the graph gives the Young modulus. That is, the graph will be straight line only when the material or the given sample obeys Hooke's law, that is within the limit of proportionality. Okay, so we'll now analyze what could be the relationship, how can we compare the stress strain graph, that is a straight line through the origin. The slope of the graph gives the Young modulus. Young modulus indicates the stiffness of the given material. Remember that. The stiffness of the given material regardless of its dimension is given by the Young modulus. Stiffness of the material regardless of the dimension of the material is given by the Young modulus. So the stress strain graph is also straight line through the origin. Force extension graph also straight line through the origin. Now we'll compare what could be the relationship between stress strain graph and force extension graph. We'll now compare, because earlier I told that when we consider force equal K times delta x, F equal K delta x, where K is the spring constant or K is the force constant, where K I told depends on the property of the material or the type of the material, and also it depends on the dimension of the sample. So K depends on the type of the material used and also it depends on the dimension of the sample. But this the K indicates the stiffness of the given object, whether stiffness of the given spring or given rod or given string, its stiffness. So even if the materials are the same, K could be different for two different springs made of the same material. But here the stiffness Young modulus does not depend on the type of the material, sorry, does not depend on the dimension of the material. It's constant for a given type of material. Remember that it independent of dimension of the material. Okay, so we know that Young modulus is given by stress divided by strain. So Young modulus is given by stress over strain. And we know that stress equal force over area, strain extension over original length or compression over original length. Same notation. So x will go to the numerator. It will become Fx over A times delta x is the Young modulus. Okay, we are going to compare the stress strain graph and the force extension graph. So we will make the force as a subject, because F equal, when we make the F subject, F is equal to EA over x times delta x. Okay, so when we consider force against extension graph or force against compression graph, this is going to be a constant for a given object. That means for a given spring or for a given wire, the Young modulus is constant, because for a given wire or object such as wire or spring, the Young modulus is constant. That depends only on the type of the material. Area of cross section of the wire is not changing, so A also constant. The initial length of the wire constant. So these all quantities will be constant. When you change the force, the extension will change. So this is going to be the K. So this we can write that equation F equal EA over x time delta x. So here this is going to be the K. EA and x are constants. Therefore we can say this is going to be in the y-axis. So we can say this as F equal K times delta x, where K is EA over x. So when we earlier we came across the spring constant of a spring or force constant of a elastic material, K is the spring constant or force constant, and we told that K depends on the type of the material, that is K depends on E. Also we said that K depends on the dimension of the material, that is K depends on area of cross section of the wire if it is a wire, or area of cross section of the wire used to make the spring, that is the A. X is the total length of the wire or total length of the wire used to make the spring, that is X. So K depends on the type of the material and the dimension of the material used in the sample. So F equal K delta x, where K is the force constant or spring constant. Okay, so earlier I told that when we plot a graph of force against extension, if it is a longer wire, when we consider two different wires, I just did that. When we consider two different wires, both have same area of cross section, both are made of same material, but one is longer, that is this is x2, this is x1, x2 larger than x1, then I said x2 that will be that will have a lower k. That I said when the length becomes larger, that will have lower k, less stiffness. I told that is true, because when the length of the wire becomes larger, denominator becomes larger, k will become smaller. Same way I compare two different wires, both have same length, both are made of same material, but one is thicker. One wire is thicker means the thicker wire will show larger stiffness. Thus, this is A1, this is A2. If A1 greater than A2, this will have greater stiffness than this. That means this will have greater K than this. That is true, because A becomes larger, K will become larger. So the wire, even they are made of same material, The wire with large area of cross section will have greater stiffness. So this relationship, the same thing, K equal EA over X gives the relationship between the spring constant of a spring and the dimension of the spring, or force constant of a wire or rod and its dimension, that related to the Young modulus of the material used to make the spring or wire, that is the E. Okay, so this is a stress strain graph. Here also the first portion is a straight line, that is up to L, that is the limit of proportionality. The material obeys Hooke's law, or the stress is directly proportional to strain, or force is directly proportional to strain, force is directly proportional to extension, up to the limit called limit of proportionality, that is marked with capital L. Then the next point is EL, that is the elastic limit. So up to this limit of stress, when the applied force is removed, the material will return to the original shape. Now there's a new thing called Y, yield point. Yield point means beyond that point, the graph will start to become more horizontal, or it start to bend more parallel to the strain. That is what is yield point means. Beyond that limit of stress, for a small change in stress, there will be larger change in strain. That is the yield point. Beyond that limit of force or limit of stress, for a smaller change in stress, there will be larger change in strain. Okay, so we consider the graph. I'll draw it again separately. The graph is bending and becoming more towards horizontal, towards the strain axis. So the graph is something like this, then bending like this and like this. So this is the point we mark yield point. So beyond that point, when we consider a smaller change in stress, you can see the change in strain is larger. Smaller change in stress, this is the change in stress, but the change in strain is larger. So if they ask what is yield point, beyond that limit of stress, for a smaller change in stress, there will be larger change in strain. That is the yield point. Okay, then ultimate tensile stress or breaking stress, the material is breaking here, but the breaking stress I already defined, that is the maximum stress the material can withstand. So that is this one. This is the breaking stress, not this one. This is the breaking point. So when it reaches the breaking stress, the molecules, when you stretch and when the material reaches the breaking stress, the slipping plane will slip, and there will be at the slipping plane the atoms will get entangled, so they will become weaker. After that, if you apply a smaller stress also, the material will break. But the breaking stress is the maximum stress the material can withstand before breaking. So this is the breaking stress. This highest peak is the breaking stress. Okay, next thing is elastic strain energy or elastic potential energy. When we deform a material, solid material, whether compress or stretch, whatever we do, when we compress the material or stretch the material, we are doing work on it. So the work done will be stored in it in the form of elastic potential energy or elastic strain energy. For example, when you are stretching a spring, you are doing work. The work done by you will be stored in it in the form of elastic potential energy or elastic strain energy. Same way, when you compress a material, compress a spring also, work is done, so energy is stored in it. Same way, a wire, when it is stretched, you can hang a wire, a metal wire, and when you attach a weight at the bottom of it, so it will extend. So when it extends, work is done on the material due to extension. So there will be energy stored in it in the form of elastic potential energy or elastic strain energy. So we know that work done is given by, we learned that in mechanics, work done is given by force into distance moved. We define the work done is equal to force into distance moved along the direction of force. Normally those questions, force remains constant. You would have done questions like wooden box or a box is pulled on a horizontal floor by applying a force of 10 Newton and it is moved through a distance of 20 meters. Find the work done. So the box is moved through a distance of 20 meters by applying a force of 10 Newton parallel to the ground. Imagine there is no friction. So the work done is given by force into distance moved. Force is 10 Newton, distance moved 20, you will say 200 joules. Right, okay, there's nothing wrong. But when we think about a spring or something like a wire or rod, we know that when we are stretching a material with a spring or wire or rod or compressing a material like a spring or rod, the force won't be constant. F equal K delta X. If the material obeys Hooke's law, the force is given by F equal K delta X. The distance moved is delta X. The distance moved, that is the amount of compression or extension, is delta X. So there the force won't be constant every time when we compress it. When the amount of compression changes, when we apply a particular force, it's gradually getting compressed. So the force is changing when the amount of compression also changing, or when you are stretching a material, when the extension changes, the force also will change. So there the force is not a constant. Force is changing with the amount of compression. So since the force is changing with the amount of compression, we need to actually integrate to find the total work done. It's given by delta W, not in your syllabus integration, delta W, K X into dx, 0 to x. This is will integrate because the force F equal K delta X, but K delta X divided by X is a variable. So this is the small amount of further extension, not in your syllabus, I am just showing it. So that's the way the total work done is given. So the reason is here, the force is not a constant. Normally what we learned in mechanics, this type of questions, the force remains constant, but here the force changes when the extension changes also. So that's the reason the final equation is in your syllabus. You must know the energy stored in the material when it is compressed through X or stretched through X. The total energy stored in it or the total work done is given by total work done or energy stored in it, that is the elastic potential energy, we normally denote by IAL, is equal to half F delta X, where delta X is the amount of compression or extension. There will be a factor half that comes due to integration. Also, we know that F equal K delta X, therefore work done when it is compressed or stretched, that is the elastic strain energy given by half F delta X, F equal K delta X. So half K delta X times delta X, that is half K delta X squared. So these are the two equations we use, that is the work done or the energy equal half F delta X or half K delta X squared. But remember, the condition to use these equations, that the material obeys Hooke's law, that is the force directly proportional to extension. If the material is not obeying Hooke's law, you can't use this equation. So remember that again. The condition to use this equation, the material, whether spring or wire or rod, whatever it is, that must obey Hooke's law. Otherwise, you can't use these equations for the energy stored in it. Okay, when we consider force extension graph and when the material obeys Hooke's law, the graph will be a straight line through the origin. So the area under the graph gives the energy stored in it, because area gives half into base into height, that is half F delta X. That is the energy, elastic strain energy, elastic potential energy stored in it. So we know that if the material obeys Hooke's law, we can use the equation half f delta x or half k delta x squared if the material obeys Hooke's law. There also, if you find the area under the straight line, we will get the equation same as half f delta x. But if the material does not obey Hooke's law, or even an elastic material that extended beyond the limit of proportionality, they are also, for example, I told that rubber never obeys Hooke's law. Start of this lesson I told that rubber never obeys Hooke's law. For rubber, the graph will be something like this. So here also area under the graph won't satisfy this equation, but here also area under the graph, here also the area under the graph gives the energy stored in the rubber. Remember that again I am telling. When we consider rubber, the graph does not obey, the rubber never obeys Hooke's law, so there won't be any straight line portion, but the graph will be a curve. But the area under the graph, even if it is not a straight line, area under the force extension graph or force compression graph will give the energy stored in it, but that area won't satisfy this equation, but the area under the graph gives the energy stored in it. Elastic strain energy we can calculate by finding the area under the curved graph. Even for a material that obeys Hooke's law, but when we stretch the material beyond limit of proportionality, the graph won't be a straight line further. They are also, initially it could be a straight line, then the graph becomes like this. They are also, the area under the graph, here also, the area under the graph gives the total energy stored in the material even when it passes beyond the limit of proportionality. But here, when the material moves beyond the limit of proportionality, it won't satisfy this equation. But when we find the area under the graph, that will be equal to elastic strain energy. So whenever you are given a graph, force extension graph, that graph is not a straight line, no problem. You can find the area under the graph. That will give the energy stored in the given sample. You can't use the equation if equal, the energy equal half f delta x. You can't use if the graph is not a straight line, but you can find the area under the graph that gives the energy stored in the given sample, that is the elastic strain energy or elastic potential energy. Now you might ask how to find the area under the curve. We don't have any equation. If it is a graph like this, we have standard equation half into base into height. How to find the area under a curve? Yes, there is a method. It's an approximation method. It's not 100% accurate, but the exam board, they accept it. I'll tell you now how to find the area under a curve. Okay, so we need to find the area under this curve. It's an approximate method, but we can use it in the exam. How do we do? We count the number of squares. The squares indicates the grids of the graph paper or grids given on the graph sheet. So we count the number of squares below the graph. Okay, and we count like this. If the square below the graph covers half or more than half of the square, we take it as a one full square. Remember that if the square below the graph includes half or more than half of the square, we take it as one full square. If it is less than half of the square, we take it as no square. That square is not included, 0. We number it. If it is full, more than 50% of the square below the graph, we take it as a one full square, we put 1. If it is less than half of the square below the graph, we take it as 0. Then we count the number ones and we find the area like this. Okay, now one by one we'll see. When we consider this first square, the grid, more than 50%, because if it is like diagonal, that will be half. The graph is covered taking more than half of the square, so we'll take it, this is covering full, so we'll put 1. So this is completely, this square is completely below the graph, so 1. This is also completely below the graph, 1, 1, 1. Now think about this this portion of the square, this is much smaller than half, so we put it as 0. So there is no contribution from that square to the area, so we put 0 because the area below the graph of this square is less than 50%. Now when we consider this square, in this square the graph is passing here, more than 50% of the square is given to the area under the graph, so we'll take it as 1. Same way this also 1, this also 1, this 1, same way this completely below the graph 1. Okay, same way now think about this square. This square, the contribution to the area under the graph from this square is less than half because only this portion which is much smaller, so 0. But when we consider this square, yes, slightly at the almost eye level half, this is more than half, so the area provided or contribution to the area under the graph from this square is more than 50%, so we'll take it 1. This also more than 50%, we'll take it as 1. This is 1 because more than 50%. But when you consider this square, the contribution of this square below the graph is less than 50% because passing through 0 here almost at the center, so this is less than 50%, so 0. Now how many ones are there? So we can say total area under the graph . 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 into area of a square. That's the way you find the area under the graph. Okay, so now different properties of solid materials. First one is stiffness. Okay, stiffness indicates how much it can resist or oppose the deformation. So in terms of graph, when you consider if you are comparing two different type of materials, we should consider the Young modulus. So stiffer material will have greater gradient than the next material. Say if you consider stress strain graph and there are two graphs, one is this way, the other one is this way. Imagine this is P, this is Q. So the material Q is more stiffer than material P because it has greater gradient. Same way if you consider two different objects made of same material or different material, better use force extension graph. Therefore, if you are comparing the stiffness of two different objects, this is two different materials, they might be made of different materials. They are made of different materials. So Q, P, when you consider material Q is more stiffer than P because it has greater gradient. But you might have two different objects made of same material or different material. There you should compare the force extension graph, the object which has greater gradient force extension graph. Say for example this is X, this is Y. We can say the object X is more stiffer than object Y because, or you can name them X, Y, or here also you can say LM. So the object L is more stiffer than object M because it has greater gradient. When you compare two different objects, their stiffness, better think about force extension graph. If you compare two different materials, consider stress strain graph. Second is ductile material. What do you mean by ductile material? Means material that shows larger plastic deformation under tensile force. Under tensile force is called ductile material. A material that shows larger plastic deformation under tensile force is called ductile material. Copper is a good ductile material. When you consider two different graphs, there it could be stress strain graph or force extension graph, larger plastic deformation. Say one material shows a deformation like this, the other material shows like this. So this is material P, this is Q. the material QP is showing larger plastic deformation. You know, this is the limit of proportional, slightly the elastic limit. You know that the straight line portion is ending here. This is the elastic limit. Beyond elastic limit, there is a larger plastic deformation. So P is a good ductile material than Q because it's showing larger plastic deformation under tensile force. Good example for ductile material, copper. Next thing is malleable material. Malleable material means material that shows larger plastic deformation under compressive force. So the shape of the graph will be the same. Earlier, when I consider ductile material it will be force extension graph. If it is a malleable material, force compression graph. Mostly, copper is a good example for both malleable material as well as ductile material. The graph will be the same. So here the material P is showing larger plastic deformation under compressive force. If it is a ductile material, it's a extension. This is compression for malleable material. So P is a good malleable material than Q because it's showing larger plastic deformation under compressive force. Good example for malleable material, copper. Copper could be, now copper shows both behavior. That means copper could be beaten into different shapes, or copper could be easily rolled into sheets because copper is a malleable material. Remember that copper is a good malleable material. That's the reason easily copper could be rolled into sheets or beaten into different shapes. At the same time, copper is a good ductile material. That's the reason copper could be pulled into wires easily because it's a ductile material. Okay, next thing is brittle material. Brittle material means it could show little amount of elastic deformation, but it never shows plastic deformation. Brittle material never shows plastic deformation, but it can show little amount elastic deformation, something like a glass. If you have a glass sheet, if you apply a force, imagine you have a glass table. This is a glass table, the upper part. So if you apply a little bit of force, or if you keep a heavier weight here, the glass can bend little bit. After that it will break. When you apply force is removed, before it's breaking, it will come back to the original shape. So the material that shows elastic deformation little bit, but it won't show any plastic deformation. Good example, glass and ceramic. If you plot a graph of force against extension or compression, stress against strain, whatever it is, force against extension or stress against strain, the graph will be like this. There will be a straight line portion, but very small plastic deformation. That is brittle material. Almost no plastic deformation. We can say no plastic deformation. Okay, next thing is tough material. Tough material means that should show larger plastic deformation, but here we say the material that must be able to absorb large amount of energy when it undergoes plastic deformation. That is called tough material. So that means the area under the graph under plastic deformation should be larger. The material must be able to absorb large amount of energy before breaking when it undergoes plastic deformation. Mostly the mountain climbing ropes must be tough materials because when the person falls, it should absorb the loss in GP becomes kinetic energy when the person falls. So it should be able to absorb the kinetic energy and should not transfer the energy back to the person. When a person falls, the climbing rope should not show elastic deformation. It must show plastic deformation because it should absorb the kinetic energy of the falling person, and after absorbing the energy, the climbing rope should not transfer back to the person because he will start to oscillate. So it should undergo plastic deformation. So the tough material must be able to absorb large amount of energy when it undergoes plastic deformation. Even car buffers must be tough materials. So if you plot a graph, force against extension or stress against strain, it will be same as earlier what I drew for copper, like a ductile material, the same format, the same shape it comes. But here we consider area under the graph should be larger because it should be able to absorb large amount of energy. So area under the graph larger. There could be a material that must be something like this. So this is not a, this is PQ. Q is a good tough material because it shows large area under its plastic deformation. So it is a tough material. Generally, composite materials are tough materials. Even copper is also a tough material, but generally composite materials are tough materials. Good example, climbing rope. Okay, strong material means the material with higher ultimate tensile stress or breaking stress is called strong material. When you consider two different materials, stress strain graph, one graph is like this. The other material is like this. So this is P, this is Q. The P has larger UTS, ultimate tensile stress or breaking stress. So P is stronger than Q. It should have highest or larger breaking stress compared to Q. P has larger breaking stress. So P is a stronger material. Then seventh one is hard material, hardness. Hardness is something related to surface. It cannot be shown by a graph. That means difficult to scratch. The material that resists the scratching, that is called hard materials. So the hard material means it's a surface property. Harder material, more difficult to scratch on its surface. Good example, diamond. Diamond is the hardest material because difficult to scratch on its surface. Hysteresis is the property of polymers, good example for rubber. That means when you stretch and release a rubber, the rubber gets warmer. For example, when you load and unload a rubber, we know rubber never obeys Hooke's law. So if it is a force extension graph or stress strain graph, when you stretch a rubber, there won't be a straight line portion. So loading means when you apply force and stretch the rubber, even within the elastic limit, the graph will be a curve like this. Right, we put an arrow like this for loading graph. Loading graph means you are applying a force and the material is being stretched. Now when the applied force is removed, if the rubber is not passing the elastic limit, it will return to the original shape. So finally the extension will become equal to 0, but it will not obey the same path. For example, if it is a metal wire or spring, this is for spring, or metal wire or metal rod, if you have loading graph within the elastic limit, the graph will be a straight line this way, that is the loading graph. Unloading graph, when you remove the added weight, it will return to the original shape. When the force becomes 0, extension will become 0, so the graph will exactly overlap. But for rubber, when you unload, even within the elastic limit, the graph won't overlap. The graph will be below something like this shape. So that means for spring and metal wires, when you consider loading graph, area under the graph is the energy supplied to it. When you release it, it will release the same amount of energy. That means if you have a spring, this is a spring attached to a trolley, a light spring, that means the spring has no weight, is attached to a trolley, and you keep the the spring touches the wall, and you compress the trolley something like this. The spring is fully compressed and it's released. So when the spring is fully compressed, the total work done by you, for example, if it is 10 joules, the total work done to compress the spring is 10 joules. When you release, the 10 joules will be given to the trolley as kinetic energy if there is no friction. If you imagine there is no friction, The practical you are doing is you are compressing the trolley, and the total work done by you, that is the elastic potential energy stored in the spring during compression, is 10 joules, and when you release it, the 10 joules, the work done by you and stored in the spring, will be given as kinetic energy to the trolley when it is released. But rubber is not like that. You are stretching a rubber to project something, a stone, or project a toy rocket. The total work done by you may be 10 joule when you are stretching the rubber band, but when you release it, the toy rocket will get not 10 joule, maybe 8.2 joule. So 1.8 joule is lost. That is the area between the two graphs. But when the rubber releases 8.2 joule, it will return to the original shape. There is no plastic deformation, but the energy it transfers to the projectile will be less than the energy you supplied to the rubber when you are deforming it. The reason 1.8 joules is lost to surrounding in the form of heat. When the rubber is stretched and released, a certain amount of energy will be transferred to the surrounding in the form of heat. That is called hysteresis. That behavior is called hysteresis. That property is called hysteresis. So the amount of energy lost to the surrounding is the shaded area. So this is the loading graph. This is the unloading graph. How to find the area? You find the area, as I told, counting the number of squares, as I told now. Find the area under the loading graph. Then find the area under the unloading graph. The arrow is this way, is the unloading graph. Then subtract, you will get the area between the loading graph and unloading graph. That's the area of the shaded portion. That is the energy lost to the surrounding. In the past paper, they gave the graph, loading graph and unloading graph, and they asked, how do you know the rubber never undergoes plastic deformation? You can say the unloading graph returns to the origin. That means when the force becomes zero, extension becomes zero. That means the rubber is within the limit of within the elastic limit. Even for metal wire, they can give a graph like this with two arrows and ask, how do you know the metal wire does not show plastic deformation? You can say when the force becomes zero during the unloading graph, extension is becoming zero. Then what could be the shape of the graph if there is plastic deformation? I am going to show it now. Okay, so this will be the graph for rubber when it has a plastic deformation. When the rubber passes beyond the plastic deformation or elastic limit, the graph will be like this. That means there will be a permanent deformation. When the force becomes zero, there is a permanent deformation. There is a permanent extension. Same way for a metal wire. This is the loading graph. This is the unloading graph. This is the loading graph. This is the unloading graph for rubber. Here there will be a permanent extension. Even when the force becomes zero, there is an extension. Almost these two lines will be eye level parallel. Okay, so here this method is used only for copper wire because copper is a good ductile material. It shows reasonably large extension that could be measured. The extension could be measured by using meter rule. Okay, so the practical setup is like this. Complete the setup. So this is a table. There's a pulley, a wire passing through a pulley and carries a pointer. There we should attach a known weight. First we should measure the diameter of the wire without applying any force. That means without this weight slot. Measure the diameter of the wire at different points at different orientation. Different points at different orientation. The wire should be rotated and measure the diameter at different points at different orientation because the wire might be compressed. So different points at different orientation by using micrometer screw gauge and find the average diameter D of the given copper wire. Then complete the setup as shown. Record the initial position of the pointer, then apply, then you should measure the total length of the wire. So total length of the wire X without any weight must be measured. Total length, normally we use 2 meter length. That's the total length, we use 2 meter. From here to here, up to the pointer, total length must be measured. That normally use 2 meter or 1.5 meter. Then apply different known weights and the wire will extend. So you must know the initial position from the ruler. When you apply force, the pointer will go down. You know, by subtracting you can measure the extension. So apply different force, and for each force measure the corresponding extension. That's all practical. Okay, how do you check whether you are not passing the elastic limit? You have a reading after you apply a weight, then remove the weight, and if it returns to the initial reading, the pointer, if it goes back to the initial position or initial reading, that means when you add a weight, there will be extension. When you remove the weight, if the pointer returns to the previous reading, that means you are within the elastic limit. You are not exceeding the elastic limit. Okay, so like that, different applied force measure the corresponding extension. Now you can analyze this raw data. You know the diameter, you know the initial length, you know different forces, you recorded different force, the applied force, and for each force you measure the relevant extension. So now you are going to find the Young modulus. So you are going to plot a graph. You can plot two different graphs, either force against extension graph or stress against strain graph. I'll explain the both. Okay, the first thing is you can plot a you can plot stress against strain graph. For that, you recorded several readings for applied force and the relevant extension. Divide each force by the area of cross section. So you know area of cross section is equal to pi d by 2 squared. So divide each reading of the force by area of cross section. You will get the tensile stress, that is force over area. You will get the tensile stress. Then divide each extension by the initial length x, that is strain, delta x over x. Find the relevant strain. Okay, you have now calculated values, tensile stress and tensile strain. You know Young modulus equal to tensile stress over tensile strain. Tensile stress equal Young modulus time tensile strain. So this is in the form of y equal mx format. Plot a graph of tensile stress against tensile strain. You will get a straight line through the origin. Find the gradient of the graph. That will give the Young modulus. That is first way of analysis by using the raw data we recorded. The gradient of the stress strain graph gives the Young modulus. Gradient of the linear portion, we didn't pass the elastic limit. I told how to check it. Okay, the second method. This is one method. This is you will get full marks. The second method, plot a graph force against extension. How to, either way, not both, either way. One is stress strain graph, or you can say you don't need to calculate stress strain. So just use force and extension. You know the initial length and the diameter and area of cross section. You know that Young modulus is equal to stress over strain. Stress gives force over area. You know area is pi d by 2 squared over extension over original length. It's going to be fx over a delta x. So you are going to plot a graph of force against extension. So make the force subject. F is equal to EA over x into delta x. So plot a graph of force against extension. So it will be on the y-axis. This is the gradient. This is the x-axis. You will plot a graph of force against extension. You will get a straight line through the origin. Find the gradient. So the gradient is equal to EA over x. So I'll write it here. Gradient I'm writing here. So gradient M is equal to EA over x. So the E, that is Young modulus, equal to gradient times x over a. From this we can find the Young modulus. This is second method to find the same data but by plotting force against extension graph. Okay, since copper is a good ductile metal, we can use the previous method. We can measure the extension by using meter rule. But if it is like an aluminium wire or steel wire, they are not good ductile material. Larger force is applied and also the extension is very small. So we need a special apparatus called Hooke's law apparatus. So there the Hooke's law apparatus has two divisions. One is called main scale, other one is vernier scale. The vernier scale can slide on the side of its groove with each other. So the vernier scale on the right side can move on the main scale. Okay, so this is the test wire. We are going to measure the Young modulus of it. This is a reference wire that holds the main scale. This is a fixed weight. This weight is variable. Here also, first, without any variable weight, you should measure the length of the test wire as I described earlier. The steps are exactly the same. We should measure the length of the test wire without any force. We should measure the diameter of the test wire at different points at different orientation by using micrometer screw gauge. Find the average diameter. So you could be able to find the average area by using A equal D by 2 pi into D by 2 squared. Also, you know the initial length of the text wire X. Now what we are going to do, we apply different weight slots and we measure the extension by using we should take the initial reading of the vernier scale and the main scale without any applied force. Then we apply a force, so the main scale will remain at the same position. When the test wire extends due to the applied force by the variable weight, the vernier scale will move down due to the extension. So by subtracting the initial reading and the final reading from the initial reading, you can find the extension of the test wire. So you know the force you applied, you know the extension, so you can tabulate force and extension. Okay, then several readings you can take. So here also the analysis exactly same as earlier what I explained for copper wire. You can plot a graph of stress against strain. It will be a straight line through the origin. Same approach as earlier. Find the gradient, that will be the Young modulus. Or you can plot a graph of force against extension. Find the gradient. The gradient will be equal to EA over M. Gradient M will be equal to EA over X. And from that you can find the Young modulus. Either way, here also we can analyze. Analyzing the data is same as earlier copper wire, only the apparatus is different because extension is lower, because both aluminium and steel wires, they are not good ductile materials. Okay, before starting questions, we'll summarize. That's all the theory. I'll summarize it. First equation we came across is the Hooke's law equation, that is force is directly proportional to extension, or F equal K delta X. For springs we call K as spring constant. For other elastic materials we call K as force constant. Then we learned that is Young modulus, capital E, is defined as stress over strain. It could be tensile stress over tensile strain or compressive stress over compressive strain. Also, we know that sigma equal force over area and epsilon equal delta X over X. This is tensile force over area, then tensile stress, compressive force over area, compressive stress. Same way, extension over initial length, this is tensile strain. Compression over initial length, that is called compressive strain. We learned that already. Then we came across the relationship between the K and Young modulus initial length. We learned that K is equal to EA over X, but they don't give this in the equation sheet. Remember, they might ask you to get a relationship, or you better know that because K depends on the type of the material, that is Young modulus, area of cross section and the length of the wire. Then we came across that the energy stored in the material, elastic strain energy, when it obeys Hooke's law, is given by EL is equal to half F delta X or half K delta X squared. These are the equations we learned in solid materials. Now we'll start questions one by one. Okay, first question, very simple question. Spring constant of a spring is 40 Newton per meter. What will be the extension when the tensile force is 20 Newton? Use the equation F equal K times delta X. Force is 40. Force is 20. K is 40 times delta X. Delta X will be equal to 20 over 40, that is 0.5 meter. Okay, second question. P and Q are two identical springs. They are kept parallel to each other and a force of 40 Newton is applied both together. P and Q are identical springs. And the extension of the system means the whole system means both together. The extension is 20 centimeter. That means each spring has extension of 20 centimeter. Find the spring constant of the springs. Each spring, find the spring constant. Each of them has, both has same spring constant. Okay, so here 40 Newton is applied. So force on each spring will be, you know, if you think about the free body force diagram, this is the attached weight. So tension on each spring is same T. The tension we normally use here F are the tensions. So 2F is equal to, so if I answer 2F is equal to, the F is the tension, 2F is equal to 40 Newton. So F is equal to 20 Newton. So force on each spring will be 20 Newton. And also the extension of each spring is 20 centimeter. Now use F equal K delta X for one spring. 20 equal K into 20 centimeter means 0.20. Find the K, that will be equal to 100 Newton per meter. Okay, so this is two springs P and Q. They have different spring constants. K1 of the spring P is 80 Newton per meter. The spring constant of the Q is unknown. Both are light springs. They don't have weight. When they are attached in series like that and 20 Newton force is applied, the total extension of the system, means the same force, they have no weight. So the tension of the spring Q is 20 Newton, tension of the spring P also the same 20 because weight of Q is negligible. So the force acting on P is only 20 Newton. So the extension of the system, that means the total extension is 35 centimeter. The question is find the spring constant of the spring Q. Okay, so the total extension we know 35 centimeter. We will first find the extension of the spring P because tension of the spring P is 20. Spring constant is 80. We'll use F equal K delta X for P. We'll use F equal K delta X for the spring P if I use. That is 20 equal K is 80 times delta X1. Delta X1 is the extension of P. So delta X1 will be 0.25 meters. That is 25 centimeter. So total extension is 35 centimeters. So therefore extension of spring Q, that is delta X2 will be 35 minus 25, that is 10 centimeter. The tension acting on the spring Q is also the 20. Now use F equal K delta X for spring Q. F equal K delta X for Q. If I use it, force is 20 Newton. K I need to find, that is K2 into extension 10 centimeter, 10 into 10 to the power minus 2. So K2 will be 200 Newton per meter. Okay, so this question, it says that a spring is attached to a trolley. A trolley is carrying a spring, something like this. A trolley is carrying a spring and it's compressed with a wall. So you move the trolley close and compress with the wall and you release the trolley from rest away from the wall. So the compressed spring will push the trolley away from the wall. So the first part is find the initial acceleration of the trolley. So when it is released, at that moment, what is the force acting on the spring? First part, F equal K delta X is equal to, according to Newton's second law, F equal ma. So that will be the initial acceleration. So K we know that is 40 into delta X is 5 centimeter, 5 into 10 to the power minus 2 equal. Mass of the spring is light. We should take nothing mentioned about the spring, so we can assume it's light. Mass of the trolley is 250 grams, so 0.5 0.25 into A. Find the initial acceleration. So that will be equal to 8 meter per second square. That's the initial acceleration of the trolley. Second part, find the maximum speed of the trolley. Here you can't use equations of motion. Some students, they try to use v squared equal u squared plus 2as. The spring, when it releases from the wall, the distance moved at the moment when the spring is returned to the original shape is the amount of initial compression 5 centimeters. Some students, they tell v squared equal u squared plus 2a. They say v squared, we need to find u is 0 because initially it released from rest. They use the same A as 8. No, you can't use, because when the spring returns from the compression, gradually the spring return to the original shape, the compressive force on the spring will change, so acceleration will change. If the acceleration is changing, you can't use it as 8 because v squared equal u squared plus 2a is when you use, it must be a constant acceleration, but the acceleration is going to change when the spring is released and when the spring returned to the original shape from the compression of 5 centimeter gradually. So the force, compressive force will change, so the acceleration will change. So the only way we can calculate is by using energy equation. So when the spring is released, when the spring is compressed, the spring carries elastic potential energy that will be converted to kinetic energy when the spring completely returns to original shape. So we can say loss in elastic potential energy will become gain in kinetic energy of the trolley. Loss in elastic potential, the loss in elastic potential energy is the initial elastic potential half k delta x squared is equal to gain in kinetic energy, that's the final kinetic energy, half m v squared minus half m u squared, but u is 0, initially it was at rest. From this we can find the v. So half into k, we know that is spring constant of the spring is 40, and the compression 5 centimeters, 0.05 squared equal to half into mass of the trolley is that is 250 gram, so 0.25 times v squared minus 0, initially it was at rest. Find the v. Everything you know, you can find the v here. So you will get v will be 0.63 meter per second. That's the maximum speed. Okay, so here a spring is carrying a weight mg. The energy stored in the spring is capital E. Similar three identical springs are connected as shown in figure. So these springs are identical to same as this one. So similar three identical springs are connected in parallel as shown in figure 2, and a total force of 2 mg is applied together to the system. What will be the energy, total energy stored in the system in terms of capital E? Here the energy stored is capital E when the force is mg. Here three identical springs are connected in parallel and a total force of 2 mg is applied. What is the total energy stored in the system in terms of capital E? So that is the question. Okay, so here we can use the equation E equal, energy is equal to half F delta x. So that is going to be half, the force is mg, so mg delta x. Okay, we know that here the force acting on each spring will be 1/3 of 2 mg, because the 2 mg will be shared among the three springs. If you draw the free body force diagram for this system, so this is the force, total force applied by the weight attached to mg. All three are identical, same as this spring, so that means nothing is mentioned of the spring constant, but if I take the spring constant, this one k, each of these springs have the same spring constant k. So the extent, the tension on each spring T, we normally use F for tension in this topic, F. So the force acting on, or the tension on each spring is F. So 3F is equal to 2 mg. So the force acting on one spring is equal to 2/3 mg. That is, the force is 2/3 of the force acting here. We know that they all have the same spring constant. So F equal K delta x, or F is directly proportional to x since all have the same spring constant. So here the force is 2 by 3 mg, means extension of each spring in this diagram, figure 2, extension of each spring will be 2 by 3. Here if I say delta x, it will be 2 by 3 delta x, because force is directly proportional to extension. When the spring constant is the same, force has become 2/3 of this force. Here the extension is delta x, so here the extension will be 2 by 3 delta x. So energy stored in one spring, E1 is equal to half. The force acting on it is 2 by 3 mg. Half F is half F delta x. I am going to use half into F is 2 by 3 mg into delta x. Delta x again 2 by 3 delta x. Half F delta x. Force acting on one spring is 2 by 3 mg. Extension of each spring is 2 by 3 mg. So the extension of one spring is 2 by 3 mg. So total energy of the system, I should multiply it by 3, E1 into 3. So that is half into 2 by 3 mg into 2 by 3 delta x into 3. Because there are 3 springs, that will be the total energy of the system. Now this 3 and 3 will get cancelled. So I should take and rearrange this one in this format. So half, then mg times delta x times this 3 and this 3 got cancelled. Now half mg delta x, I wrote it 2 into 2. There, this 3 and this 3 got cancelled. So 4 by 3. So half mg delta x, half mg delta x E. So it's going to be E into 4 by 3. So the energy stored in the system is 4E by 3. Okay, so original length of a string is 0.60 meter. Tension in it is 190 Newton. Diameter of the string is 3.3 10 to the power minus 4 meter. Young modulus of the string is 170 gigapascal. Find the extension of the string. So we know this data, we need to find the extension. So we know that Young modulus is equal to tensile stress over tensile strain. We know the Young modulus, we know that, and the tension we know 190, and the initial length we know that, and the diameter we know that. So area of the cross section is pi d by 2 all things squared. So we find the area. So that's going to be pi, diameter is 3.3 10 to the power minus 4 by 2 all things squared. So that will be 8.55 10 to the power minus 8 meter squared. That is the area of cross section. Okay, so this is force over area over extension over original length. It will become Fx over A delta x. That is the Young modulus. So we need to find the delta x. From this delta x is going to be Fx over EA. So we'll find the delta x. Delta x is going to be force what is applied is force is 190 Newton. The initial length of the string is 0.60. The Young modulus is 170 giga 10 to the power 9. And the area of cross section 8.55 10 to the power minus 8. So solve it, you will get the answer 7.84 10 to the power minus 3 meter. Okay, so this is the stress strain graph. Stress is in megapascal, strain is 10 to the power minus 3. It's drawn for spider silk. The stress strain graph is for a thread of spider web. An insect hits the web, exerts a tension of 580 micronewton. The thread extends by approximately 3% of the original length. Find the radius of a single thread of spider silk. Okay, from the graph, stress strain graph, the linear portion, it's actually given on a grid. This is a only a part of a question. This is the old past paper question, January 2015. This is from January 2015, question 16, WPH 0101 question. Okay, so I didn't give the full part, it's only a part of it. So from the graph, it's on a grid, so I took only the clear points. We can find the gradient of the linear portion that gives the Young modulus. So Young modulus equal gradient. So Young modulus capital E equal gradient 36 into 10 to the power mega. So power 6 minus 0 over 25 into 10 to the power minus 3 means 0.025 minus 0. So you will get answer that is 1.44 10 to the power 9 Newton per meter square. That's a Young modulus. Okay, so we know the strain. Thread extends by approximately 3% of the original length, means delta x over x equal to 3%. If you give it in value 0.03, normally we don't use 3% in the equations. We need a decimal value, so that is the strain. Strain is equal to 0.03. We know the strain is equal to 0.03. Okay, so the force applied is 580 micronewton. So we know that Young modulus equal tensile stress over tensile strain. Tensile stress means force over area over extension over original length. That is the strain. We know the value of strain. Young modulus 1.44 10 to the power 9 is equal to force. We know 580 micronewton 10 to the power minus 6 over area of cross section. We don't know, we need to find, that is pi r squared over, this is 0.03. so the only one unknown is pi r squared. So from this we can find the pi r squared and find the r, solve it. You will get r is equal to 2.07 10 to the power minus 6 meter. That's the question. Find the radius of the thread. Okay, so the next question, May 2017 WPH01 IAL paper, that is question 18. There are 3 diagrams are given when a flea jumps. I'm not writing the question, so you can see the exam paper, May 2017 WPH01 question 18. In an investigation of a jump of fleas, measurements were taken from a high-speed video. The body of a flea can provide maximum power of 660 watts per kilogram. So that's the question says. The body of a flea can provide a maximum power of 660 watts per kilogram. A part, a flea of mass 0.7 milligram. So they are saying a flea of mass 0.70 milligram takes 0.85 millisecond to take off from rest. Show that maximum velocity of the flea is about 1 meter per second. So they are saying the power provided by the flea is 660 watts per kilogram, but the mass of the flea is given 0.70. So the power given by this flea, the mass of the flea, which is 0.70 milligram 10 to the power minus 3 kilogram, milligram, that is they are saying 660 watts per kilogram. 10 to the power minus 6 milligram to kilogram, because they are giving the power is given by 660. The question says 660 watts per kilogram. So this is milligram. So converting milligram to kilogram, 0.70 10 to the power minus 6 into 660 watts. So this is the watts given to the flea by its muscles. That is given by 4.62 10 to the power minus 4 watts. So this is going to be the kinetic energy. So the time, we know that power into time, that's the energy given, is equal to gain in kinetic energy. So power into time, 4.62 10 to the power minus 4 into time is given as 0.85 millisecond. So 0.85 into 10 to the power minus 3 seconds is equal to kinetic energy half the mass of the insect. Again we need to convert to kilogram, 0.70 10 to the power minus 6 kilogram v square. That will be the kinetic energy. So from this, find the speed v. That will be 1.06 meter per second. That is the A part of this question. Okay, B part, calculate the average acceleration of the flea. The flea took off from rest. So the average acceleration A equal V minus U over T. So the final speed we calculated 1.06. Initially it was at rest. The time taken also given, which is 0.85 milliseconds. So 0.85 into 10 to the power minus 3 meter per second squared. So that will be equal to 1250 meter per second square. That is the acceleration of the flea from the initial stage until it leaves the ground. That is the A part. Sorry, this is not B part. That is the A part. Second part, what we calculated earlier, that is the maximum velocity, which is 1.06, is the A part first part. This is A part second part. Now the B part includes a projectile motion. The measurements were repeated with many fleas. The average initial velocity of the fleas at takeoff was 1.2 meter per second at 39 degree to the horizontal. Calculate the average horizontal distance moved. So this is the projectile motion. So if you draw the diagram for projectile motion, so the initial average speed is 1.2 meter per second at an angle of 39 degree. So when we consider for the whole motion, so they asked to find the range. That's the question. So this is the question we need to find. What is the range of it? Okay, so for the whole motion, this is nothing related to solid matter. This projectile motion, B part. This question for the whole motion, I can use vertically S equal ut plus half at squared. So the vertical displacement, when I consider initial and the final thing, they are along the same horizontal, means it went up, came down. So vertical displacement 0. Initial vertical velocity is 1.2 sine 39 into t plus half. The gravitational acceleration is downwards. So I am taking upwards. So minus 9.81 t squared. So here t squared, this is 0. Whole equation could be divided by t. So 0 equal 1.2 sine 39 minus half into 9.81, 4.905 t squared. They get cancelled. So the t is gone. Now t squared becomes t. Solve it. Bring it to the left and solve it. You will get time that is equal to 0.154 seconds. This is the flight time, 154 seconds. Now I need to find the range. For the whole motion, use horizontally, S equal ut plus half at squared. I need to find the range. So the initial horizontal velocity, I need to find it. That is 1.2 cos 39 into time is 0.154. Horizontally, no acceleration, so 0. Solve it. That will be the range. That is 0.144 meter. That is the range. Okay, so these diagrams are given part C. It says that when a flea jumps, some of the energy comes from the leg muscles and some from a compressible pads behind the leg, behind the back legs. The pads are made from a protein called resilin. Before jumping, the pads are compressed. On takeoff, the pads expand rapidly, transferring energy to the back legs of the flea. You can assume that each pad is a cube of sides. So that's the diagram they have given. Cube of sides, 60 micrometer. Micro means 10 to the power minus 6 micrometer, which fully compressed. So before jumping is fully compressed until the depth of the pad is negligible. So it's fully compressed in the first diagram. So before it jumps, it's fully compressed and the energy stored in it is given as the kinetic energy. So the first part of this part says that for a particular jump, the total energy transferred, so the total energy transferred, that is total energy transferred from the pads and the leg muscles is 0.80 microjoule. Calculate the percentage of energy for a jump that comes from the two pads. Young modulus of wrestling, Young modulus of wrestling is given as 1.8 10 to the power 6 Pascal. That's the Young modulus of this material. Wrestling is 10 to the 1.8 10 to the power Pascal, and the strain of it 1.0. So we need to find the percentage of energy for jump that comes from two pads. The total energy is given 0.80 microjoule. So I need to find the energy stored in this one. So energy stored, if I want to find, I know the Young modulus, I know the strain, we know half F delta X is the energy. I need to find the force that applied to completely compress the wrestling, these pads, how much force is required to fully compress through 60 micrometer. Half into that force into delta X, compression is 60 micrometer. That will be the energy stored in one pad. So two pads, they are saying two pads involved during jump. So I need to find the total energy from the two pads. That energy divided by this energy into 100 is the final answer. So I need to find the force. So we know that Young modulus is given by force over area over strain, that is given, like strain is directly given, so I don't want to write it as delta x over x because it's directly given. Okay, so I need to find the force. Area is 60 into 60 micrometer into micrometer. So I can write the force I need to find. F is equal to E cross multiply E into A, because this A will come down. So it will be the denominator. If I write again, F over A epsilon cross multiply Young modulus into strain into area of cross section is the force. Okay, so Young modulus we know that 1.8 10 to the power 6, strain is 1, and area of cross section 60 into 10 to the power minus 6 micrometer. Again multiply, so I can put square, it's a square, this much of Newton. Find the force. So you will get force 6.48 10 to the power minus 3 Newton. So energy stored in it, energy stored in one pad half F delta X. So I know the force 6.48 10 to the power minus 3 into delta X is 60 completely compressed, 60 micrometer 10 to the power minus 6 joules. So solve it. That will be so there should be half into 6.48 10 to the power minus 3, 60 into 10 to the power minus 6. So that will be equal to 1.944 10 to the power minus 7 joules by 1 pad. So percentage from 2 pads, that is 2 into 1.944 10 to the power minus 7 over the total energy 0.80 microjoule, 0.80 10 to the power minus 6 into 100. So that will be equal to 48.6%. Okay, so I hope you understood this complete lesson. You can pass your comments if you want. So yes, I think it's useful to you. That's the end of complete lesson in solid materials. Okay, we'll meet during the next lesson. Bye.